Hello everyone. So here is again we are going to see continued part of design of RCC continuous beam. In previous session we have seen how to take load from slab on beam. We have started with this numerical. We have to design continuous beam A, B, C, D, E. This is what is the data given. This is how we have identified type of slab and cross section of beam. Then to do the load calculations, we have calculated trial depth and effective span. Then we have calculated dead load. Dead load includes load from slab. So here in this case, which I have missed in the previous session, this is self weight, equivalent self weight from the slab plus 1 we have to add for floor finish 1 into B, that is the floor finish over here. It is given as 1 kilonewton per meter square. So herein we have to add 1 into B, that is width of strip. So thus we will be getting it as the total load. So this I'll do it over here, this plus 1. So this we will be getting it as 11.33 kilonewton meter, and thus dead load includes load from slab, which includes self weight of slab plus floor finish. So we have considered this, and accordingly we will be getting total dead load as 26.4 kilonewton per running meter. Live load we have calculated equivalent slab load from both the sides, and we will be getting factored load. Now once we have identified with dead load and live load, that to factored dead load and factored live load, this is factored live load, we are having now, we have to do analysis of beam. For analysis of beam, we can see the beam which we have considered, it is having same span, 1 2 3 4 4 spans we are having, and it is having 4 meter each span. So span variation is less than 15%, 15%. At the same time, it is surrounded by the slabs which are giving same load on the beam. Whether I will be considering S1, S8, I will be considering S2, S7, but it is giving same load on span AB and span BC. It means this particular beam, it is having same load throughout. So we are having now uniformly distributed load over here. This each span, it is having same UDL, and at the same time it is having same span. This is 4 meter, this is 4 meter, and on 4 meter and 4 meter, right? So when we are having such a case that loads on each span and span having variation less than 15%, then the bending moment values or shear force values or analysis we can do using the codal provisions as given in table number 12 of IS 456. Now where I am in IS 456 2000, table number 12. If you want, I can show you, page number is 36. So what this table number 12 it is giving? So these are the bending moment coefficients. What is the meaning of this bending moment coefficient? So we know when we are having a simply supported beam subjected to uniformly distributed load, its bending moment is WL square by 8. WL square by 8. It means WL square into 1 by 8 is its coefficient. Now here in this case we are having this as continuous beam, okay, and for this continuous beam, as just now I have mentioned, when we are having span variation and loading variation less than 15%, we can directly take that values from the table 12. If it is not means what? If the variation, loading or span variation, it is more than 15%, then we have to use methods of analysis of indeterminate structure, that is continuous beam. For example, we can use in that case moment distribution method. Even in case when such a span is there which is having combined loading, like it is having uniformly distributed load and at the same time if it is having point load, in that case also this table number 12 we cannot use. We have to use over there moment distribution method or any other method. You can use slope deflection method, you can use flexibility method, stiffness matrix method, any method one can use over there. But here since we are having, again I am repeating, span variation and loading variation less than 15%, in that case we can use table number 12. So let's go once again to the table number 12. Here in this case now we are having, since this is a continuous beam and which already we have discussed, we have to consider span movements which are sagging movement and we have to consider support movements which are hogging movement. So span movements are positive movements and support movements are negative movement. We have to consider separately for dead load and fixed imposed load, and we have to consider not fixed imposed load. So here in this case you can see near middle of end span and at middle of interior span. So let us first identify the points. Which points we require? Middle of end span, middle of interior span and over support. So I'll be identifying first the points. Let we will consider this. A is our simply supported span, so it will be, the moment is 0 over here. At center we are having, this is mid span, so let us consider this moment as M1. Over support, this is support B, so here let us consider moment is MB. This is second span. At mid span, I'll be considering this as M2. At mid span, here it is, I'll be considering M3, and here it is, I'll be considering M4. Over support we are having, this is support C, this is support D, so we are having over here MC and we are having MD. In this way now we are having M1, M2, M3, M4 are mid span movements. It will be at mid span. Mid span again means what? It is the sagging movement, means it is the positive movement. And over support means we are having MB, MC, MD are the hogging movements, means these are the negative movements. Now let us identify near middle of end span. Near middle of end span, we are having for dead load it is 1 by 12 and for imposed load it is 1 by 10, means for live load it is 1 by 10 and for dead load it is 1 by 12. So you can see over here at middle of end span, so this is end span and this is also end span. If I am going from this side, this is end span. If I am moving from this side, this is end span. So we are having now moment M1 should be equal to M4. M1 should be equal to M4. and I'll be considering this as mu1. This as mu1. And what are the coefficients we are having? First we will write it as alpha d. If it is a coefficient for dead load, then this coefficient should be multiplied by what? For obtaining the bending moment, the coefficient shall be multiplied by the total design load and effective span. So we are having now total design load. If I'll be considering over here WD, or we have written it as WUD as the total load, as the intensity of load, then total load will be WUD into L by into L. Again we have to consider the movement, so we have to consider it as WUD into L square, plus we are having, or we have to consider for live load. So for live load coefficient is alpha L, and we are having WUL, that is live load into L square, into L square. Okay, so here in this case we will be having it as alpha d is how much? So let us go to the code. It is 1 by 12. Alpha L is 1 by 10. Okay. So this is 1 by 10 into WUD is how much? So we have already calculated it. WUD is equals to 39.6. This is 39.6. Oh, it is 1 by 12. 39.6 into L square. L is 4 meter. So this is 4 square, plus this is what is for, we did it for dead load. Now we have to consider imposed load. It is 1 by 10. So this alpha L is 1 by 10 into WUL is how much? It is factored. We have calculated it at 16. So we are having this into 16 into 4 square. In this way we will be getting this as 78.4 kilonewton meter. This is what is the moment. In this way we have to do it for all the points. What first we have to consider? It is middle of end span. Now next is what? It is middle of interior span. Now this M1, M4 is middle of end span, and M2, M3 is middle of interior span. Okay, so we'll do it now. As I have explained earlier, this is what we are getting it as. How much we will be getting? 78.4 kilonewton meter. Now just same way tell me how to write for this M2 and M3. So again we have to consider this as alpha D into WUD into L square, plus alpha L into WUL into L square. Now at M2 and M3 are what? M2 and M3 are the middle of interior span. And what are the coefficients? 1 by 16, 1 by 12. So let us consider this. 1 by 16 into WUD is 39.6. 39.6 into 4 square, plus alpha L is, we have seen from table number 12, it is 12 into WUL is 16 into L square is 4 square. So this is what we will be getting it as 60.9 kilonewton meter. This is sagging moment. This is sagging moment, right? Now we have to find out support moments. Support moments, what are the points we have to consider? At support, next to end support, and at other interior supports. So let us go to the diagram. What we are having? At support, next to end support. So A is our end support, B is support next to end support. If I'll be considering E as end support, then D is support next to end support. It means now MB and MD are the support next to end support. And in that case, what are the coefficients given? 1 by 10, 1 by 9. What is this minus sign indicates over here? This indicates negative moment over support. So this is 1 by 10, 1 by 9. Okay. So this I will be taking minus totally outside. We are having alpha d WUD L square plus alpha L WUL into L square. So this is over here minus of 1 by 10 into 39.6 into 4 square plus alpha L is how much it was? It is 1 by 9. 1 by 9 into 16 into L square, it is 4 square, and thus we will be getting this as minus of 91.8 kilonewton meter. Okay. Now which point remains over there? At other interior supports. So if we refer to the diagram over here, we are having A and E are end support, B and D are next to end support, and C is the other interior support. So what is the value for other interior support? You can see minus 1 by 12 minus 1 by 9. So on the same line I will be doing over here. Now I am not going to write this equation again. I will be directly writing now. It is minus, I will be taking outside or common. It is 1 by 12 into 39.6 into 4 square plus for live load it is how much it was? 1 by 9. It is 1 by 9 into 16 into 4 square, and this is be minus 81.24 kilonewton meter, right? So amongst these four values, irrespective of its sign, amongst this we are having maximum as this 91.8. Don't consider that it is a minus 91, so it is less than plus 60.9. No, it is not like that. Minus sign or plus sign, it only indicates in what manner that beam is bending, it is deflecting. So positive means it is deflecting in sagging way, and negative means it is deflecting in hogging way. Okay, so in this way we have calculated movement at all the points. So you can see when we are having such a symmetrical loading, symmetrical span, it is quite easy using or referring IS 456 table number 12 to calculate moment value. Otherwise, what we are supposed to do? We have to calculate these moment values using moment distribution method. Of course, I am going to show one numerical wherein we are going to analyze continuous beam using moment distribution method. Fine. Now once we have identified with moment, now we have to find out the values of shear force. Again on the same line, same fundamental, variation of loading and span less than 15%. So directly we can use IS 456 table number 13. So herein we are having table number 13, and see what are the points. At end support, at support next to end support, herein we have to consider outer side, inner side, and at all other interior supports. At all other interior supports we have to consider the value. So we will be now doing it. Let us go to the diagram. We have to identify end support. So this is, say, VA is the end support. Here it is B. This is next to end support. What is the at support next to end support? And we are having outer side and inner side. So we will be having over here, if this is total VB, I will be writing, then VB outer side, and this is what is VB inner side. Okay. Now we are having this as end support B, C, D and E. So if this is a end support VE, this is next to end support, and from this side, this is outer side, this is inner side. So this is VDO and this is VDI. VDO and VDI. Here it is VA. I'll be writing over here. Now what? Now we have to consider all other interior supports. So only one support is remaining over here. It is VC, which is other interior support. Same way now, when we are calculating shear force values, we will be multiplying it by total load. So if I will be considering a simply supported beam subjected to uniformly distributed load, what is its reaction at support? So if this is W, if this is L, then the support reaction V is equals to W into L is the total load divided by 2. It means here we will be having factor as 0.5 into WL. Total load is W. It means this coefficient we have to multiply it by total load. So on the same line, now we have to see what are the factors or coefficients given for all these different points. So let us consider at end support. End support means we are having, end support means we are having A and E. Okay. Next to end support B and D, and other intermediate support VC. Okay. So at end support VA and VE, it is only for one time I will be writing alpha D. It is WUD into L plus alpha L into WUL into L. Okay. So how much is the alpha D mentioned? How much is the alpha D mentioned? 0.4 and alpha L is 0.45. So this is 0.4 into 39.6 into 4 plus alpha L is 0.45 into WUL is 16 into L is 4. So this shear at end support, it is, we will be getting it as 92.16 kilonewton. Same way now we will be finding, we will be calculating it for the considering symmetry. VBO should be equal to VDO, okay, and VBI should be equal to VDI. VBI should be equal to VDI, okay. And for that, outer side we are having 0.6, inner side we are having 0.55 and 0.6. So let us calculating this. So let us calculate this. What we are having, VBO and VDO, alpha D, that is 0.6 we have seen. So it is 0.6 into 39.6 into 4 plus 0.6 into 16 into 4, and this value comes out to be 133.44 kilonewton. 133.44 kilonewton. Same way now to calculate for inner side, 0.55 and 0.6 were the coefficients. So this is 0.55 into 39.6 into 4 plus this 0.6 into 16 into 4. So this comes out to be 125.52 kilonewton, and at other interior support the value is, let us see, 0.5 and 0.6. So this 0.5 into 39.6 into 4 plus 0.6 into 16 into 4, and this value is then equal to 117.6 kilonewton. Done. So this is what is the reaction or shear at every point. Amongst this you can see this is what is the maximum value. Either we can design for maximum value or we can design it separately for separate span. So what is the procedure we have carried out till now? We have to design continuous beam ABCDE. we have identified its trial depth, then effective span, then we have calculated loads, and then we have analyzed beam. Analyze beam means what we have did? We have calculated moment at positive moment at midspan, negative moment over support, and we have calculated reactions, that means shear values at different points. Is this clear? So this is what for now, because after this we have to start with actually our design of beam, and that design now we are going to see in the next session. So